So in this video, we're gonna discuss about callbacks and TensorBoard in Keras. So we're gonna explore how the monitoring training visually using TensorBoard and dynamically adjust the learning rates and log metrics to CSV, and we can even schedule learning rate dropouts. So these are required to boost performance, stability, and reproducibility. Here we're gonna use Fashion MNIST dataset, load the dataset, configure the train and test splits. After that, next we build a fully connected model using Keras sequential API. We'll compile it with Adam Optimizer and categorical cross entropy because it's kind of one hot encoding, and we're going to use accuracy as a metric. This model is simple, but it will help us focus on training behavior through callbacks. So Keras callbacks allow us to tap into training at key moments. Therefore, before and after each epoch, before and after each batch, and on training at the start or at the end. In this example, we're gonna use 4 powerful callbacks. Therefore, TensorBoard, Reduce, LR on, Plateau, CSV Logger, and Learning Rate Scheduler. So after training the model, you can see that the validation accuracy and the training accuracy, and this the validation loss across. Here we can see that the learning rate is good, and this is the TensorBoard. Here we can control to before the start of each epoch, after the start of each epoch, and we have achieved accuracy around 88%. That's not bad. Thank you. So in this video, we are gonna discuss about Keras tuner for hyperparameter optimization. So it's essentially a kind of automated hyperparameter tuning in TensorFlow. Instead of manually guessed layer sizes, dropout layers, or learning rates, or else training models up to model by trial and error, Keras tuner helps you to find the best configuration intelligently, which can be reproducible, and it's kind of efficient. So import the required libraries and then load the test and training splits of the dataset, and this is the dataset with different labels with 10 different classes. So we use Hyperband tuner, which is efficient and smart because it runs early stop for short trials first and then allocates more time to promising candidates. It's faster and cheaper than grid or random search. You can also try a random search or Bayesian optimization or sklearn, scikit-learn tuner for classic models. So we're going to do early stopping to avoid overfitting, and then we're gonna do the tuner.search. So this launches the hyperparameter sweep. Basically, it runs dozens of mini trainings and logs performance and also scores trial using the validation accuracy and narrows down the best configuration. Here we can see that this is the best configuration. So once we have the best parameters, we build the final model. So you're gonna notice that the model is trained faster and performs better, and it's gonna overfit less because Keras tuner did the guesswork. So moving on to the model curves for accuracy, and here the Test accuracy of the model is 88%, which is pretty good. So these are the predictions. It almost correctly predicted all the things correctly. Thank you. Let's moving on to data augmentation using um, Keras CV. So first we install the Keras CV, which provides state-of-art augmentation techniques like cut mix, mix up, and random augment, and more, all with minimal code. So we'll import the TensorFlow, Matplotlib, NumPy, Keras layers and models, and then we load the Fashion MNIST dataset, which is a common benchmark for vision models. We do essentially three pre-processing steps. Therefore, normalize images to 0 and 1 range, and expand dimensions to add a single channel for 2D layer, and one hot encoding, which labels using to underscore categorical function. So these are the sample images. We build three training datasets, therefore baseline, which has no augmentation, just shuffle and batch. And whereas cut mix augmentation, in this we're going to randomly replace a region of image with a patch from another image, and labels are also mixed proportionally, and the mix-up blends two images and their labels together. So this results in soft targets and smoother decision boundaries. For both cut mix and mix-up, we use dot map to apply them to batches. This step alone adds a huge amount of regularization power without requiring any architectural changes. So we can see that our simple feed-forward CNN has flattened layer, dense layer with 128 units plus kilo, and report rate with 0.3, and final softmax layer. This is perfect for comparing the effect of data augmentation. Same model is trained across all three setups with 10 epochs. So after training the all three models with the same configuration, we can see the training and validation accuracies for all three models in one plot. Cut mix and mix-up may slow early convergence slightly, but often improve final prediction accuracy and reduce overfitting. Here we can see that cut mix may struggle slightly with small datasets or low resolution images, whereas a mix-up gives modest improvement and smoother predictions. And also the baseline performs well, but with the risk of overfitting on smaller dataset.